Hello and welcome once again to Baked Beans Garage, where it's time to make the ice cubes. Here I have a working automobile with a fresh engine, but I'm still fat and sweaty, so I need air conditioning. Let's work on that. If you're new to the channel, this is the 1986 Volvo 740 turbo diesel wagon I've been working on forever now. Last time I got the fresh new D24T that I rebuilt running, only with major complications, and there's still some custom work to do on the other side with some tubes for the intake and the catch can. But before I go putting more aftermarket pipes in there, I want to get the rest of the factory pipes in here, so that means time to get the AC working. So I wanted to use this opportunity to make a video explaining how the AC works, how to service it, how to troubleshoot it, how to fix it for the people that might not be familiar with the system. So before getting into the nuts and the bolts in the car itself, some theory is required, so to the whiteboard. So here's a little crash course on heat and air conditioning as it applies to cars. The conservation of energy tells us that energy cannot be created or destroyed. It can only change forms and locations. And that's all heat is kinetic energy. So if we want more of it, we gotta get it from somewhere. If we want less of it, we gotta put it somewhere else. So beginning with heat, heat's easy. We already have something in our cars, for the most part, that's making excess heat. All we gotta do is take some of that coolant that gets the heat from the engine, put a little radiator in the cabin, blow air across it, and you got heat for your defrost and warming your giblets. So no matter the substance, heat is stored in the molecules by them jiggling and zooming about. This coolant here, you can tell it's coolant because it's green. These molecules are jiggling and moving around. You can tell because of my animation lines. So if we were to touch this coolant to another substrate, be it another fluid like air or a solid, or perhaps the oil in your oil cooler, these molecules are going to bonk down into this wall or whatever barrier you have and make these molecules start jiggling too, thereby transferring the heat energy, making all this warmer and making all this cooler. That's called conduction. It also works across air, which is called radiation, albeit much less efficiently because the molecules in air are all spread apart, not like a solid or a liquid here. So when you turn your heat on, the excess heat from the combustion jiggles the molecules in the coolant, helped along by the heater core making the surface area much greater for more contact with the air and more heat transfer. And then you get your heat out, thereby cooling the coolant, warming the cabin air, and sending that back to the engine to go get some more heat. So in this setup, we can look at both the engine and the heater core as heat exchangers. The engine puts the energy into the coolant, and the heater core takes it out and transfers it to the cabin air. Very simple. Air conditioning, on the other hand, is much more complicated because we need to take the heat energy from the cabin air and dump it somewhere else. And we can't dump it in the engine, it's already hot. Can't dump it outside because that's already hot. So physics and science must be applied, and I'll have to draw a different picture. So to understand exactly what the AC is doing in your car, first we have to go over some physics. So here's a totally unqualified lecture on that. For illustrations purposes, I have taken two cylinders here, put a piston on top, and filled them with some gas. Don't worry about what it is. My molecules also aren't to scale, but those are molecules. So this gas over here, it's pretty cool. Molecules are all spread apart. They're not jiggling all that hard. But if we were to compress this by shoving that piston down, that's going to squeeze all those molecules together, and they'll start running into each other and jiggling a lot more. So by reducing that volume by moving the piston, our volume goes down and our temperature and pressures both go up. And then we arrive over here where we can see that also the opposite is true. If we drew that piston back up, volume's going to go up, temperature and pressure are both going to go down. Now, if we were to wait a while this is compressed, the new heat energy caused by the compression is going to radiate out if it's able to, if the surrounding environment is cool enough. And eventually those molecules will calm back down to the room temperature we started at over here. So now imagine that this is where we started, and this is our ambient air and ambient temperature, and we draw that piston back up and come back to what looks like over here. Now that there was less heat energy stored in that volume to begin with, now that we have increased that volume by drawing the piston up, our pressure and temperature will once again fall. And now we have arrived at a situation wherein we have that same air, but it is now colder and has less energy in it than when we started. So this will then be able to absorb more heat and cool down its environment again. And this principle can be made a whole lot more efficient by using a refrigerant and latent heat. So latent heat is just the term used to describe how much energy is in something versus its state of matter, so solid, liquid, or gas. And here's a colorful little diagram ripped straight from Google to help visualize that relationship. So we'll use water as an example. Everyone knows water. It can be ice, it can be liquid water, and it can be gas in the form of water vapor. Obviously, it has the most energy when it's gas, a little less when it's a liquid, and the littlest when it is ice. So on the vertical, we have the temperature of said substrate, and on the horizontal, we have how much energy is in it or is being put into it or being sucked out of it. So if we want to make some ice out of water vapor, we start with a gas, and in order for it to become a liquid, we need to take some heat out of it. So we chill that down, pull the heat out of it, and it eventually condenses into a liquid, which is where it is here. And if we keep sucking energy out of it, it'll eventually freeze down into a solid. So by doing that, we're just pulling the heat out of the water and moving it through its different phases of being. On the contrary, if we have some ice and we want to make some water vapor, we gotta put some heat into it. So you warm up your ice, it eventually melts into a liquid, thereby absorbing heat from its environment. We keep making it warmer and it'll eventually vaporize or evaporate. Again, this graph applies to pretty much any substrate you could imagine. One you're most familiar with is probably spray paint or brake clean. When you spray your paint or your brake clean onto a thing, you may notice it gets cold as that evaporates. And that's exactly what you're seeing here. The substrate is sucking the heat out of its environment in order to turn into a gas. Similarly, since the boiling point of water is directly tied to the atmospheric pressure, if we apply pressure to that gas or to that liquid, it'll skew this whole graph up in that direction. i.e., it's going to take a whole lot more energy to turn that liquid into a gas. And that's how pressure cookers work. It just puts pressure on that water and then it takes a whole lot more energy to turn that liquid into a gas. That way you can get your water a lot hotter than its normal boiling point and cook stuff in it without it boiling. There's also a cheat code called sublimation, whereby certain materials can go straight from a solid to a gas and absorb a whole lot of heat while they do it. And that's what dry ice is. It's solid carbon dioxide that at normal room temperature and atmospheric pressure, it can go straight from a solid to a gas, suck up a bunch of heat, and make really cold. So to apply those principles and make them useful for air conditioning, we need to use a refrigerant. And a refrigerant is just a compound that can quickly transition back and forth between a gas and a liquid, moving around heat while it does that. So if we return to my original doodle with the two cylinders and the pistons, although this time full of a refrigerant instead of a mystery gas, if we shove that piston down and compress that refrigerant, this container is going to get hot because those molecules bouncing off each other a lot faster now. And the important part is that we compress this to a pressure where it naturally wants to become a liquid again, but it can't because there's too much energy in it. So it's going to remain a gas until that heat leaves. So if we run some air or coolant or something cooler across there to carry that heat away, that's going to suck up enough energy to allow that refrigerant to condense back into a liquid. So at this juncture, we have a liquid refrigerant that we have added energy to by compressing it, and then let that energy escape by letting it cool and condense back into a liquid. Now, if we are to expand it again by drawing the piston up, or rather allowing it to expand, because this is still at a higher pressure, we can come back over here. And because of the drop in pressure, that liquid is going to turn back into a gas by vaporizing. And if you remember from before, it takes energy to go from a liquid to a gas. So as this expands and evaporates back into a gas, it's going to suck in heat from anywhere it can get it. So this container is going to get really cold. And as it continues to cool its environment, it'll eventually get warmer and warmer until we're right back to where we started before we compressed it to begin with. So now to make this into an air conditioning system, all we have to do is separate the condensing cycle from the evaporating cycle. Then we can have one thing get hot and one thing get cold, and the refrigerant is constantly doing exactly that, pumping heat. So now that I have made a very simplified drawing of an air conditioning system, let me introduce you to the main characters. Here is a compressor, represented as just a simple piston compressor with two check valves at the top. This spins around, makes a low pressure into a high pressure. Over here is the condenser, which takes that high pressure gaseous refrigerant from the compressor and expands its surface area through its many fins and passages and allows it to throw that heat off into ambient air. Of course, air is moving across both these heat exchangers. And as it throws that heat out, it's going to condense back into a liquid. So out of the condenser, we have a high pressure liquid coming over here to the expansion valve. This is just a very specific sized hole, what provides resistance for the compressor to build pressure behind. And as the high pressure liquid crosses that restriction, it's going to become a low pressure liquid and then go up in here to the evaporator. So now that the refrigerant is a low pressure liquid, it's going to want to turn back into a gas. And to evaporate, it needs a bunch of energy. So it's going to travel through the evaporator somewhere buried down in your dash, and as the blower motor blows air across it, it's going to suck up all the heat it can from that ambient air as it evaporates back into a gas. And as it comes out of the evaporator, once again a low pressure gas, it can be compressed again by the compressor into high pressure, back through the condenser and through the whole system again, and around for eternity, making this end hot and this end cold, pumping the heat from here to there. Now, a useful side effect of the cooling from the evaporator is that as it sucks all the heat energy out of the ambient air, it also sucks the heat energy out of the water vapor in the ambient air, thereby making it want to condense back into a liquid itself, which is why on a real hot and humid day, you will see some water dripping out from underneath your car, and that is just the humidity in the ambient air being condensed off of the air going into the cabin. That way you get out cool and dry air, which is useful because I'm told humans use evaporative cooling themselves to stay cool. As the human body makes sweat, that sweat evaporates, thereby sucking up heat energy with it and cooling down the human. Although in that application, sweat is acting more like a coolant than it is a refrigerant. I don't know. Still a very ineffective system. I think it could use for a redesign, but at least for air conditioning systems, that helps humans stay cool. And again, this is a super simplified version of an air conditioning system. I will now reconfigure this to make it more representative of what you might find in a car. So here it is laid out in vaguely the same geography as what we're going to look at on the car. First and foremost, since we need some mechanical energy to impart onto that refrigerant to drive the compressor, we already have the engine that's spinning, so we'll just borrow some of that with a belt. Not shown in the last drawing were the pressure switches and the service ports. Off the high side of the compressor, where we have the pressure line going to the condenser here, somewhere in that system you're going to have a service port and maybe a pressure switch. There's a few different configurations you can have, but for the sake of illustration, we'll have two pressure switches. Then out of the condenser, we have the line that goes back towards the firewall to the expansion valve, which is typically right in front of the evaporator. That way this line stays nice and hot, and you're not absorbing heat energy before you need to or want to in the evaporator. This is down inside the HVAC box in your dash. Got a water drain here, what goes ideally out to the ground. What I didn't show in the last drawing is the receiver-drier, so we got a new character here. Now, I'm not going to get into the chemistry that makes it important, but you do not want any water in this system because that plays very unkindly with your refrigerant and makes acid or something. I don't know. The receiver-drier is just a can full of desiccant. Desiccant just sucks up water like the little flavor packet in the beef jerky that they tell you not to eat. Then coming off the receiver-drier, we have another low-pressure sensor and another service port. So, now, inside the compressor, there's some metal bits spinning around and moving past each other. That obviously needs some lubrication. And with a vapor cycle air conditioning system like this, the lubricant is just shoved in there with the refrigerant and it flows around the system. So the compressor has a magnetic clutch on the front, which picks when the compressor is being driven and when it's not. And typically the electrical signal for that clutch will go through one or both of the sensors. That way your clutch can only engage when there is a residual pressure already in the system. Now, I'm not going to get into vapor pressures and when the system's off, what's liquid where and all that nonsense. But the important thing to know is that when it's off, it's still going to have a residual pressure. And when you turn it on, this pressure is going to be low. This pressure is going to be high. Which brings me to my other point, the service ports. So to properly service this system, we need to look at the pressure on both sides of this system. So here we have a manifold gauge, which is just some tubes and some gauges. And that lets us see that the compressor is not only making pressure, but also making suction, because the pressure differential across the expansion valve is what makes all the magic happen to begin with. And we'll see this in action later, but just so you're prepared for where the things plug in and what they do. Furthermore, this is how we both introduce new refrigerant into the system, but also, very importantly, how we dry vacuum on the system. More on that later, but we need to draw a vacuum. All right, bear with me. Just be thankful you're not the one editing my ramblings. The refrigerants themselves. Pretty much all you're going to see anymore in reference to cars is R12 and R134a. R12 is the old stuff, 134a is the new stuff. This started being phased out in the early 90s, so if you have a car, I don't know, 93 or 94 newer, it's going to be 134a. There's also R1234yf, which is the new stuff, but we're not going to talk about it. If you're watching my channel, you have an old shit box. Don't worry about any of that. So here's a rough sketch of those two molecular structures. Now, I don't have the science and chemistry type of neurodivergence. I have the mechanical and electrical kind, so I'm not going to pretend I know what all that means and why that makes it a good refrigerant, but that's what they look like. Again, my molecules are slightly larger than scale. The important thing to note is that R12 has chlorine in it, and that is very bad for both your lungs and the ozone layer. 134a will still kill you, but it's not quite so bad for the planet, which is nice. Still illegal to release either of them into the atmosphere, so don't do that. But I'm a YouTuber, not the EPA. Now, differences between these two systems. Your service ports are going to be different. R12 systems, you'll see these threaded AN type flared fittings. 134a has these click-on type. You can assume red's the high side, blue's the low side. So when converting to 134a, those need to be adapted. But the big problem going from R12 to 134 is that this molecule is physically smaller than this molecule. And older standard rubber hoses, these molecules will just creep straight through the walls of the hose and eventually leak down over time. So 134a requires a specific 134a barrier type hose to keep those guys in there. Also in R12 systems, you'll see standard black O-rings and some flare fittings. Same issue there. Teeny tiny molecule, it can leak through those O-rings and past those flared fittings. 134 systems, you'll pretty much only see O-ring fittings, and there are specific O-rings which are blue or green or not black. More about that later. Now, common misconception that 134 is less efficient than R12. That is not true. Pound for pound, R134 is the more efficient substance. It can transfer more heat more quickly. But when you have a system that's designed to run R12, the system itself can become less efficient with 134a. That's because 134 just runs at higher compressor discharge pressure, and it takes longer to throw that heat off and condense. So if you have an older, specifically European car, supposedly BMWs are pretty bad with this, their condensers were already just big enough, so when you need the condenser to do more work, you end up with a weaker AC system. However, with older American land yachts with enormous capacity AC systems, that's pretty much never an issue. With this Volvo, we will find out. It looks to be a fairly big condenser. I don't know. I'm sure there's math and science that could be done to tell me specifically how this system will perform, but I'm not going to worry about it. Also, because 134 has a lower molecular weight, I don't know. It's a different compound. It might not need the same charge level. We'll talk about that when we actually put the refrigerant in the Volvo. So to summarize, AC works with latent heat. It makes a refrigerant go liquid gas, liquid gas, liquid gas a bunch of times to suck the heat out of the cabin. You've been introduced to all the main characters, now you know these two guys as well, and have a vague understanding of the difficulties of converting between this and that. Side note, if you have R12 in your car and it works well, don't touch it. Until that goes bad, it leaks out or your compressor blows up. Just don't touch it. You need a license to work with that stuff anymore. This stuff is real, well, less cheap anymore, but you can still get it at the main stores. Anyway, that's enough of that. Let's go to the car. So now that we have vaguely a third grader's understanding of how all that fancy sciencey stuff works, we can look at the parts that actually make it happen. As I'll demonstrate later, this usually goes in a car or some kind of air conditioning system, not on a table, but for illustration purposes. Here it is. All of this will be covered in detail later, but compressor, some heat exchangers, the evaporator, condenser, these are some old ones, the new ones are already in the car. I got some hoses, what for converting these, receiver-drier, some seals, service port adapters, expansion valves, oil, all that fun stuff, along with some mystery tools that will help us later. So first and foremost, this being a 1986 Volvo, it was set up to use R12 from the factory. Throughout this video, I'll also be converting it to R134a. So here I have some hoses, some new seals, and some service port adapters. Now the new refrigerant won't matter for the hard metal parts like the receiver-drier, the hard lines, and the heat exchangers. But for all the squishy bits, we're going to need to do something. So I have this Galaxy is just the brand name. I believe it's made by Goodyear. I have some new crimp ferrules for attaching it to here, and some new O-rings. Now this compressor is a bit of a mystery. It came on the core engine that I rebuilt to put in the car, so I don't know its history. The part number is illegible, so I'm not sure what refrigerant it was supposed to use, but my guess is, because someone took the time to clean it up and make it pretty, it's probably still good. We'll see. But I'm going to begin with these soft lines because this is the part I have been dreading the most. And this is mostly still legible here. We could see it says Freon 12 right on there. And even on cars from all over the world, these standard sizes are expressed in fractions of an inch, also in numbers. I believe these are number 8 and number 10. I don't remember. It says ½ inch right there, so that's what I bought. It'll probably work. You will also see, if you are shopping for hoses, there is standard barrier and reduced barrier. From what I can tell, that just means the standard barrier is a thicker walled hose. I'm not really sure. This is standard barrier for what that's worth. They both say they hold R134a, so should be fine. Anyways, since these are permanently put together with these crimp ferrules, those have to be gnawed off of there in a very unromantic fashion, so let us begin with that. I find it most convenient to put this in the vise. Of course, human blood has iron and moisture in it, and as we know, that can cause corrosion in the AC system, so I find it most convenient to keep the blood off of this. Anyways, to excise this hard line from the soft line, we'll chuck it in there and then ever so carefully just slice that crimp ferrule, while being careful not to go too deep to damage the barb underneath. Go just deep enough where you start to see rubber in there. If you see metal again, you're kind of hosed. And now it is just a matter of peeling that away. And it will likely take quite a lot of force. There we are. And there we go, a nice preserved barb ready for a new hose. On to the next. The discharge line had this little thingy on it. I'm guessing it's a pressure switch used for a different engine transmission combination in this car that isn't used here because I can't find anything to plug into it. And I completely broke it trying to replace the O-ring, so I just lopped it off altogether. Now it's going to need a bead to hold the new hose on, so I used an admittedly archaic method to do that. After this massage, I shaved it down to a more hose-friendly bead shape and then annealed it by getting it red hot just to relieve any stresses so it doesn't crack later. It's sketchy, but I know it works from past projects. Also, I already have an idea for the little piece I cut off. It even has a choke built into it. So for getting these aluminum lines cleaned up, a little bit of Scotch-Brite and brake clean goes quite the long way, and then you can hit it with some ceramic coat or just automotive wax, and that keeps it shinier for longer. Now, for actually affixing the hoses to them, I have the proper tool for once, or at least Shenzhen, China's closest approximation to the correct tool. I might use this once a year or two, but it's quite handy. So originally these were bead lock fittings. You can see the little groove there where the ferrule used to grab onto. But here on the suction line we have these barbs which will give us a nice tight mechanical lock. So for the new ferrules, I just have some generic ones from eBay that'll work good enough. Now if you're starting from scratch, certainly lay these into the car and see how long they need to be. Mercifully here, they are going on just as they came apart, so I'm not worried about it. And you also want to use the set curl in the line to your advantage so you're not bending it backwards when you go to install it. That made sense. Yeah, probably. And of course, cleanliness is key, given how teeny tiny those 134A molecules are. And that's one done. Now yes, it's doing kind of the same job as a hose clamp, but with the pressures these systems run at, you need quite a lot more holding than a hose clamp can give you. I had no such luxury on the discharge lines, no barb, just the bead lock, so I've added a little bubble flare just for extra security. A quick way to spot a counterfeit Prada bag is that they'll never mix colors of hardware. Either you'll have gold or you'll have silver on the whole bag, never both. That being said, I'm not the happiest with that zinc finish in the aluminum lines, might do something to dress it up later, but it is certainly functional. And with that, the whole system is about ready to have its bolts put in, so I'm going to go one piece at a time and do some explanations. Guess we'll start with the compressor. So some basic anatomy first. Up here we have the pulley, which is on a magnetic clutch so the car can pick when this is driven and when it's not driven, which is how it regulates temperature and stuff. More on that later. Now this is a modern rotary style pump. This has been the standard for quite a few years now. I have taken one apart over there to see exactly what's going on in here. So starting at the front, we see here we have the pressure disc and spring apparatus of the clutch. Were I to take that apart, this is what we would find. On the front of the compressor, there's a big electromagnet, and then this, the idler pulley. There's a big bearing in there so your belts can ride on it even when it's not driven. So that goes like that. That plate goes on the front and connects to the shaft. You put power to the electromagnet and it sucks that guy down into that plate and makes the compressor spin. Said compressor, here is the pump body of one of these compressors. You can see this one was killed by some corrosion. Don't worry about that. Down in there are the bores for the pump pistons, and on the back is just some simple reed type check valves so the gases go in and out in the correct order so they can be squeezed. Driving those pistons is this wave swinger palm tree looking apparatus. I was going to make a cutaway, but that's a little too much effort for this video. This is called a swash plate. This shaft is driven, and you can see as that spins around in there, this plate wobbles back and forth and creates an axial back and forth motion of those pistons. That's the best demonstration you're getting. Just imagine that going around inside there. Good enough. But quickly, a word on oils. Earlier R12 systems use a simple mineral-based oil. R134a systems need PAG oil, or polyalkylene glycol. Sure. Mineral oil is not soluble into 134a, so it needs its own special stuff, and you don't want to mix them. They're not compatible at all. So this has been sitting upside down for a couple days to let all the old oil out. I don't even know which flavor it was. Also a fairly common misconception that PAG oil is green. You'll see that it's clear. If you see green, that's because of the UV dye that someone has added to find leaks. Okay, let's put the bolts in. And leaving the belt loose so I remember to put the oil in it later, we can move downstream to the condenser, which uses the smaller of the two flexible hoses. This is slightly complicated by my intercooler as well as my transmission cooler. Check out the last video for that and a few videos back for that and some other boosty information. So the condenser I'm using is original to the car. It's already in there because it was just convenient to do it in that order when I did the radiator and the trans cooler. And as far as I can tell, it doesn't leak because it still had pressure when I took it apart. Furthermore, there's a few different core widths, and I wasn't convinced I could find one that would definitely work. Also, being an older series flow condenser, it makes it possible to flush it out in case there's any old oil or glitter left in there. And by series flow, I mean it is for the most part one long tube that snakes back and forth throughout all these fins. And again, for the most part, because this actually has 3 separate circuits. 1, 2, 3. But the important part is it's one long tube. Modern cars have what's called a parallel flow condenser, where more like a radiator, this whole side will be common to each other, and then there will be many parallel rows what go through the other side. And since it's not a smooth tube that goes in and out, it's difficult to flush those effectively. Speaking of flushing, this is a specific AC system flusher outer type juice, just in case there's any debris or old mineral oil left in there. Now this stuff is great, but you can only use it if one, you're going to blow through it with compressed air afterwards, and two, you have a vacuum pump to suck down the system, because this is designed to evaporate off under vacuum and leave no residue, which is why it is specific AC stuff. I don't know what brands are around anymore. This is a couple years old, but should work good enough. Here we could see the smaller inside and larger outside. I'm just going to put some tube on there so I don't make a mess. And here is one very conveniently shaped bit of random coolant hose. And this may seem a bit extra, but so was painting literally everything before I put it back together. So, you know, we'll keep the continuity. And when you're putting together these O-ring fittings, keep in mind it is not a compression fitting, like a flare fitting. The O-ring is doing all the work, so they don't need to be ridiculously tight. And of course, putting them together is the easy part. If you've ever taken this type of fitting apart after 30 or 40 years, you know it can be a little dangerous and painful. Also going to have to get a little creative with the routing down in this area. What with the intercooler pipe, but we'll get to that. Moving downstream once again to the expansion valve. Here that is. If you think it looks familiar, it probably does. I believe this is originally a General Motors part. I don't know. It was used on a bunch of Chevys and Volvos and Volkswagens and a bunch of other domestic American garbage from the 80s all the way up through the mid-2000s. It came with a black O-ring, so I put a green one on there. Also worth mentioning, here is another common flavor of expansion valve. You can see that guy would capture both lines going in and out of the evaporator. Given this little tube on the end, I'm guessing that's for some kind of pressure or temperature regulation. This one's from a Mark II Golf, also used by a bunch of different manufacturers over the years. And since we're right here, conveniently the next part downstream in the system is the receiver-drier. And as with anything with a bunch of things, you gotta line up, leave everything loose till all the things are screwed into all the other things, and then you tighten everything down at once. And again, this is a super generic, common part, also used on Volkswagens, Audis, and GM products. It even came on the absolute pinnacle of automotive engineering, the Chevrolet Celebrity. You'll also see this guy right here. This is a pressure switch, what cycles the compressor on and off. I'm to assume that's to prevent the compressor from picking up liquid refrigerant, because if that happens, that can break stuff. You only want gas going into the compressor. Some evaporators, you will see they have a thermal switch built onto the evaporator. What cycles the compressor on and off? It is this guy that does that on the 740. And here's the connector for that, which has been dangling in the engine bay for about a year. Nice to finally have somewhere to put that. Furthermore, all of these receiver dryers, they will come with sealed caps on them. Since they're full of a desiccant, if you have those off and it's just sitting around, that'll be sucking up ambient moisture and you'll start to waterlog it. So leave these on until you're absolutely ready to put the thing together. Now to complete the system is the other soft line, what snakes around down to the compressor. And with all of the squishy bits done, the whole system is about ready for R134a, and it might even hold it in there if I'm lucky. The only thing left is the service port adapters. Now there are two service ports on the high and low side right on the back of this compressor. I've already stuck the high side service port on there, but that discharge line is kind of in the way to use that low side service port. But this receiver dryer has two ports on it, one of which is for the pressure switch. The other one, I'm assuming, is meant to be a service port. So for this style of valve, you just unscrew the existing Schrader valve and then thread the adapter right onto that service port. Depending on what flavor you have, you might not have to take the Schrader valve out, but just read the box. And with that taken care of, the only thing that has to be opened on the system again is the compressor, so I can put the oil in. Now, a word on oil. If you buy a new compressor or a new receiver dryer, they may or may not come pre-filled. It's always best practice to just drain that out anyway and then refill it with what you know is correct. There are two main formats in which you can buy refrigerant oil, that being a jug and a refrigerant oil charge. I like using the jug because I like to see it with my eyes going in there. And I'm not sure about other makes and models, but at least with these Sanden compressors, we have a fill plug at the top to make it nice and easy. And of course, make sure that's nice and clean. Any dirt or grit getting down there is going to be an expensive headache later. And for some reason, the best tool I had on hand to do this was a filler bottle for a Nitro RC car. And I know from the half-legible sticker on the side I need 175 cc's. And with a final clean, there goes the rest of the legible words on that sticker. Perfect. And we can finally get along to the leak check so we can meet the manifold gauge. Fairly self-explanatory. High side service port, low side service port, some gauges. The yellow tube in the middle goes to your refrigerant or your vacuum pump. With R134a, these service ports are just a typical air chuck style thing, so I'll hook those up and start sucking it down. So now that everything's hooked up, I can start pulling a vacuum on the system, but first I'll explain some more things. The reason it is important to vacuum down the system before you go charging it is because R134a and other refrigerants, when they are introduced to water or moisture in the air or in the system, that does some chemical-y wizardry and you end up with hydrofluoric acid, which will eat pretty much everything, most notably your aluminum and your seals. So you want to keep that out of there. And of course, having just put the system together, we're going to have ambient moisture still left in there. So vacuuming it out will drop the pressure enough so that all that water will boil out of there. Furthermore, that allows you to leak check it quite easily when you have vacuum on it. So back to the manifold gauge. Keep in mind that these gauges will always show the pressures of what is in the systems, meaning that is always connected to there regardless of the position of these valves. So with the yellow hose connected to the vacuum pump, I can go and open these valves. They're already open. And when I kick on the pump, you will see those needles start to creep down, indicating and vacuum. I did something wrong. Wonder what it was. Upon further examination, I can see that there's even arrows on here to help me. They were closed. Okay, now when I kick the pump on, you will see those needles come down. It's more like it. You will also see fog coming out of the vacuum pump exhaust. That is some oil from the compressor, as well as that moisture in the system coming out as water vapor. And it's best practice to just set it up like this and let that suck vacuum on it for, I don't know, hour or two, just to make sure you get all the moisture as possible out of the system. And if you don't do this, it'll still work, but then you'll have moisture in the system. You do have the Receiver-Drier to help mitigate that, but that can only do so much work. That plus the leak checkability is the right way to do it. Well, not entirely. The right way to do it would be to have a dedicated machine what can recover old refrigerant, put new refrigerant in, draw that vacuum, leak check it, do all that in one big box. Those are expensive though. This stuff is like 180 bucks at Harbor Freight, so that's what I have. So it's now been about 2 hours. We still got a vacuum. Now to leak check it, all we have to do is cut the systems off from the vacuum pump. So we'll close these valves and cut the pump off. And we'll see what the needles do. And they didn't immediately fall off to zero, so that's promising. We'll leave it sit like that for a few hours to see where we're at. In the meantime, before we go ahead and charge it anyway, we're going to have to make sure the compressor is actually going to do something, so let's look at the electrics. So everything I've talked about so far applies to pretty much any vapor cycle air conditioning system, whether it's in a car or a house or a shop or boat or whatever. The main thing that sets us apart in an automotive system is that we have to get that mechanical energy from somewhere, and here it comes from the engine via a belt-driven compressor. If this were in a dedicated system, not in a vehicle that doesn't move, you just have a motor driving this and that's easy enough. You just turn the motor on and off. But since this has no authority over how fast the engine is spinning, we need to be able to regulate it, so we don't ice up the evaporator or suck liquid refrigerant into the compressor and blow it up. And in most automobiles, that is done with a clutch on the front of the compressor, as I mentioned earlier. This compressor specifically is a modern Volkswagen one, what has a refrigerant control valve instead of a clutch on the front. And instead of just cycling the compressor on and off, it actually chooses how much refrigerant goes through the compressor versus how much is bypassed. This is all complicated nonsense, but if you're watching Baked Beans Garage, you don't have something that new, so we're not going to worry about it. Furthermore, in an electric vehicle, it is that easy to just turn the compressor motor on and off. But if you're working on an electric vehicle, you're watching Aging Wheels at the very least, not me. No matter. My point is The electrics of the system are by far going to be the most vehicle-specific part of all of this, so I'm going to cover it a little bit as it pertains to this here Volvo, but you're going to have to do some of your own research if you want to fix your own system. So I have found some drawings. So here is a simplified generic diagram of an AC system, at least how the electrons dance through it. For simplicity, I have cut out the battery and the ignition switch and fuses, whatever might be feeding the AC. This green line coming out is just, hey, I want AC. So to prevent the compressor from running when the system is empty, we will have a low pressure switch here, and in series with it will be a high end pressure switch to cut the compressor off if pressure gets too high on the high side. And instead of either of these switches, or with one of these switches, we might have a temp switch on the evaporator. In case it gets too cold, it can cut the compressor off. As far as I can tell, in this Volvo, we only have one switch, which is vaguely there in the system. But like I said, it's going to be specific to your car, so none of that might matter. So here's the diagram for this car. I have gone over in green how the power actually ends up getting to the compressor. It comes off the battery, goes through the ignition switch, down here through a fuse. One thing that you probably won't have on most cars is this delay relay, which takes a signal from the alternator, and there's a little timer circuit in there that makes the compressor wait 10 seconds after the engine starts. And right here is the pressure switch coming off the side of the receiver-drier. That seems to be the only thing in this system that's controlling the compressor based on what's actually happening with the refrigerant. That, for a B28, that's a different engine. We don't have that solenoid valve. But to simplify, when you want AC, you turn it on the HVAC control panel. That sends power to a pressure switch, and that either does or does not let that power go through to the compressor clutch. So the first thing I located on the car is that delay relay. Nope, don't worry about that, that's a secret. Here you can see I have jumped the two terminals, what open and close based on that delay circuit. Just so when I turn the switch on the dash, I'm going to immediately have power to the compressor just for simplicity's sake. Moving on to the engine bay, here we have that pressure switch on the side of the receiver-drier. That just takes power from that relay, makes its decision, and then sends power or not to the compressor. So to pretty that up, I have made the wire long and put it in its own little conduit and ran it along the low side hose over to the compressor, a little spade connector right there. I have also added its own ground coming up here to this grounding block up in the fender well. And that is because the compressor is mounted on 4 rubber bushings, so it might not have the best ground otherwise, and just for redundancy. So the easiest thing to do now is just to turn the key, turn on the AC, and see if the compressor clicks. And it's fairly loud, you'll hear it. So to get power up there, we need the blower motor on, and then it's set to one of the AC settings, so we should hear it right there. Now, being Baked Beans Garage, of course, this isn't the first time I've tried this. It didn't work the first time. And that was because of some sad contacts here. That's no good, I'll have to figure something out. But as it is right now, should be good enough to try to charge the system. So let us check on some dials. Now I ended up leaving this for about 12 hours and it hasn't leaked. I think we're good, but first, a word on refrigerants. So as mentioned briefly before, there are 3 main types of refrigerants that you're going to see working with cars. You may have heard them all referred to as Freon, although that's not technically correct. R12 is the only one that is a Freon. Freon is a trademark of the Chemours company, what invented it. Although you may see these other 2 marketed under similar marketing nonsense names. The important thing to know is R12 is the chlorofluorocarbon. It has that chlorine with it. R134 is a hydrofluorocarbon. It doesn't have the chlorine. 1234yf is a hydrofluoroolefin. I'm doing my best here. And it's basically propane, very similar chemically to propane. And if you're wondering, yes, propane can be used as a refrigerant in systems designed for it. Of course, it runs pretty high pressures. Speaking of propane, vapor pressure. And this will help explain why these little single service port CAN adapters from Extortion Auto are nonsense. They may get your system working, at least temporarily, but if you're using this thing, you probably have an underlying problem that this isn't going to help you with. And that's because this can only tell you the pressure of the low side of your system. So the only thing you really need to know about vapor pressure is that if you have refrigerant in a container, no matter how much physical refrigerant is in there, this is always going to be vaguely the same pressure. And that pressure is going to vary based on the temperature of this container. And at room temperature, the vapor pressure of 134a I think is roughly like 70 pounds. So regardless of how full this can actually is, if there's any 134a in there, it's going to be that same 70 pounds. And this is why, to know how much propane is in a cylinder, you have to weigh it. And also why, if you just look at the pressure of the low side of your system, you have no way of knowing how much refrigerant is physically in there. The only way to get the right amount is to completely evacuate it and recharge it. You also may have a sight glass, but given how complex the system is, that doesn't do you much good. Anyways, as mentioned before, the right way to do it is with a big machine and a big tank of 134a, but these little cans are easy enough to get and fairly cheap. Well, not anymore. They are getting expensive, but they're still easy to get. And with the aid of a service port adapter, I can plug that in to the yellow hose on the manifold gauge and charge it from there. So let's see if it'll start. Not sure if I mentioned yet, but you'll also see the receiver dryer called the accumulator. That's because that's where the liquid refrigerant naturally wants to settle in the system, and it also makes sure the compressor does not suck up liquid refrigerant, because that is bad. That does not compress. So normally, to charge an empty system, you would first start it and then start shoving refrigerant into it and let the compressor kick on when it feels like it. But since I know that's just going to start running as soon as I turn on the AC, I want to put some in there beforehand. So apparently I don't have the right adapter to actually plug this in anymore, so I'm just going to use the one you have to be quick with. This, of course, lets you open the can at your leisure, whereas this, as soon as you thread it on, it's going to open the Schrader valve in the top of the can. So be quick about this, and you'll hear it do some stuff. And with that threaded on and held upside down so it gets liquid up through there, I can open the low side valve, and that'll start sucking refrigerant. We also have a little sight glass. That's nice. I can see it doing something. And originally, there would have been a sticker somewhere in the engine bay, it was over there by the evaporator, that'll tell you how much and of what kind of refrigerant to charge it with. Of course, it would have said R12, but it did say 2.65 pounds in imperial for some reason. Each one of these is 12 ounces, so I suspect it'll take roughly 2.5, we'll see. Also, because of going from R12 to 134, it might take a little bit more. But that is where the science ends and the guessing begins. We'll just see what happens. And with that empty, since I know I need at least 2 cans in there, I can shut that guy back off and put another can on here. So now with some pressure in the low side, I can start it. Of course, that will probably keep taking refrigerant until it gets to its vapor pressure. But since there will be no liquid refrigerant in the evaporator, I want to start cycling it around there before I completely fill up the receiver dryer and end up getting liquid refrigerant into the compressor. So time to begin the engine. And just to clarify, I do have the exhaust running to outside, just so you don't think I have a death wish yet. We'll see if it works. And with about 2.5 cans in the system, and the high side high and the low side low, it should be cooling. I can feel here the receiver dryer is getting cool. It's a fairly cool and dry day. If it's hot and humid, you'll see that start to get some condensation on it and sweat up. We can also feel the condenser getting hot. And of course, in the car, the air is getting cold. Should have got a thermometer, but you can trust me. I promise it's getting cold. So that was a little spooky. You saw that red gauge hit almost 500 psi. That's not very good. Most R134 systems do have a high pressure cutout at around 400, so that's not tremendously terrifying. But it gives me an opportunity to talk more about heat and what turns the compressor on and off. This switch on the receiver dryer is not just a low pressure cutout switch, but also the clutch cycling switch to regulate the temps and the pressures in the system. So as we know, the higher the temperature of a vessel, the higher the pressure, the lower the temperature, the lower the pressure, and that's what it uses to control cycling the compressor on and off. So this switch is set to turn on at about 30 psi, and that's not just an arbitrary number. That is just the pressure and, by extension, the temperature at which the system knows it's getting dangerously close to start sucking up liquid refrigerant into the compressor, because once that gets so cold, it's not going to be able to evaporate, and you don't want to compress a liquid because it won't. Moving along to the high pressure switch, if there were one, that would just be a safety device. Which brings me to what just happened. Since I don't have the radiator fan in, there was no air moving across the condenser, which heat soaked, and it wasn't able to get rid of that heat. So the excess heat in the system just kept building up, as did the pressure. So it probably would have kept going. Luckily, I caught it before something bad happened. We'll just call it an impromptu stress test for my high pressure line fittings. They've held up, that's good. As mentioned before, most R134a systems will have a high pressure cutoff switch. I have now shot myself in the foot by getting rid of the spot for one. But no matter, I'll just put the fan on and see how it feels, because I suspect that won't really be an issue once it is actually put together. So I'm going to throw the fan and shroud back on just to make sure my guesstimation is correct. But it looks like the actual hard parts of the system are working properly, and I'm not going to have to do the troubleshooting that I anticipated. So back at the whiteboard, I will give a brief crash course on what those gauges mean, how to read them, and how to troubleshoot based on it. So an important thing to keep in mind is the scale of these two gauges is completely different. Your low side gauge is going to have a vacuum range and then a normal range up to somewhere around 150, but your high side gauge is going to go from 0 up to maybe around 500. So at rest, if you have that supposed 70-ish PSI, your gauges are going to look something like that. And that's showing an equal 70 PSI on both sides. And then when you start up the system, that compressor is going to suck down one side and build pressure on the other. And you should see something hopefully like that if your system's working properly. My numbers were quite high, but with all the science and latent heat and whatnot, now you know that the difference in those two pressures is what actually gives you your cooling. So it's still working. Now, once you've ruled out electrical problems and the compressor is kicking on, but it's still not cooling, by far the most common problem is just a weak compressor. With that said, the closer those two numbers are, the weaker the compressor. So if it's not building suction on one side, your low side's going to be high, and if it's not building pressure on the other, your high side is going to be low. And that's what a weak compressor will look like. Unfortunately, however, if you have an expansion valve that is hung open, it could also look something like this, but that is far less likely because the expansion valve doesn't actually have metal bits flying around in it. Now, another issue you could have is if your discharge side is way high and your low side is not equally high, rather somewhere between normal and low, that could mean you have a restriction somewhere between the compressor outlet and the expansion valve, and there is too much resistance in the system. And finally, if you just have a low charge, the compressor isn't going to have anything to suck on. Your ratio will be roughly the same, but both sides are just going to be low. Then again, this applies to literally every type of air conditioning system, so there are many resources from actual professionals on how to troubleshoot that. Furthermore, the motion of the needles can also tell you stuff. If your high side needle is vibrating back and forth, it'll dance a little bit, but if it's really wagging back and forth, that could be indicative of maybe a dead cylinder in the compressor, a bad check valve in the compressor. But typically when compressors go bad, they go bad all at once. Also, an easy way to tell is if you drain the oil out of the compressor and of course there's glitter in it, that's no good. And if that does happen, then you got to go through the whole system, replace at least your expansion valve and your receiver-drier, because there's no way to flush those. If you have a modern parallel flow condenser, you have to replace that too, because there's no good way to flush it. And maybe just try to flush the evaporator, because you don't want to tear the dash apart, and hope for the best. That's worked for me before. Anyways, let's go let that compressor breathe a little better and see where we're at. Okay, now the opposite thing is happening. The compressor is not shutting off because this switch was stuck closed. Luckily, I had another one on my parts car receiver-drier, so that is now in there. The switch was open before I put it on. It is now closed that it has system pressure. Mercifully, there is a Hank Schrader valve right in here, so we can replace that switch without having to evacuate the system. That being said, I think this condenser is doing its job just fine. With that new information, I don't think I'm going to need a high pressure cutout switch. It's still a little chilly, but once we get a nice hot and humid day, I can set the manifold gauge back up and really stress test this system and see if I get anywhere near the dangerous area. Also, since we have a mechanical fan, there's never going to be a situation where there isn't wind across that condenser, so I think I'm good. However, if I decide I do need one, I can just get rid of the high pressure service port and replace it with a pressure switch. I still have that little spade connector right there, so I can wire it in series. No matter, the system should work good now. Let's find out. Okay, the system is finally working as intended. I had the mic right there, and then I waited till the compressor was running to cut it off so you could hear the remaining refrigerant flowing through the expansion valve, just for funsies. Now again, there isn't much heat to suck out of the cabin air because it's only about 45 degrees Frankenstein right now. But we saw the compressor cycling, we see this getting cold, the air in the cabin is indeed cold, and the condenser is getting hot, so it worked good. Now again, since it's cold, you saw that the compressor discharge pressure only got up to maybe 120. But again, that was still plenty to drop the low side down low enough to cut that switch off and cycle the system. And I said this refrigerant is about 70 psi at room temperature. I would like to clarify it is not currently room temperature. So when I started it was maybe 50 psi. Can't read them from here. The next step is to just wait for a hot and humid day to really stress test this and see if I want to add a high pressure cutoff switch, but at the moment I don't think I'm going to. And in the end, I ended up charging it to right about 2.65 pounds, which is the amount of R12 it calls for. But again, we'll see how that behaves in the summer. So yeah, the system is together and it's working. So I think that wraps up the nuts and bolts of this video. And the last thing I want to do is another leak check. I'm not sure if I mentioned it, but when doing a leak check with the vacuum pump, it is possible to have a false positive or a false result of some kind. That's because if something somewhere is somehow acting as a check valve, it could be holding that vacuum by not letting air in, but once you charge the system with pressure, it could let refrigerant out. So a solution of soapy water works well around all your junctions. I happen to have a solution specifically for AC leak finding. So pretty much anywhere I had a part, I'm just gonna give a spray and see if bubbles come out. So the stuff I'm using is called Big Blue. You can find it on the interweb pretty easily. It's a little pricey, about $25 US for this 1 quart. But in my opinion, it is certainly worth having over dish soap because this stuff is super thick and goopy and stringy, because it flows nicely into all the cracks and crevices, and then any leaks that it finds show up as a real fine foam with lots of teeny tiny little bubbles. And this is an American brand. I'm not sure what equivalent you might have in your country, but just look it up. This is also an old bottle. It has a snake on it now. And after slathering every interface I touched with the goop and waiting about 2 hours, I did not find any bubbles. I'm not about to simulate a leak so you can see what that looks like, but just trust me, it is tight under vacuum and under pressure. So with everything working and not leaking, I think that brings us to an end for today. This appears at least right now to have been a successful R134a conversion, but again, we'll find out in the summer when it gets real nice and hot and humid. And just remember, I'm just some guy making YouTube videos in my garage. I am not infallible, and I'm certainly not a professional. So if you think I got something wrong, please do let me know in the comments. I can always pin comments and add annotations if I have to correct myself later. So next time I'll be finishing up the engine bay. There's a few things left to do. That being said, outro. So I filmed these outros after I've already edited the rest of the video, and oh my, this video is an hour long. So more than ever, I do appreciate you sticking around if you're still here. Next time we'll be finishing up the engine bay, making it a complete working car with all that stuff behind me. I would like to thank @TheArchitect's Garage on Instagram for this lovely new logo. He's a talented artist with a lovely aesthetic. He might draw your car if you pay him too. Do let me know if you want merch of that. That'd be neat. Anyways, I am a slightly less sweaty chinchilla. This has been Baked Beans Garage, and I will see you next time.